Hi folks, today we're going to talk about areas of circles and sectors. And before we do that, I want to just review what happened in the last lesson. In the last lesson, we tried to figure out the arc length, and that was different than the arc measure. The arc measure is the measure of an arc in degrees, very closely related to the measure of the central angle with that intercepted arc. But yesterday, we were talking about arc length, and the way you calculate arc length, or the actual lateral distance from one point to another on an arc, the way you calculate arc length is you create a proportion. And a proportion typically compares things with different units. In our first ratio, we talk about units with degrees. So we have the arc measure over the entire measure of the circle in degrees. And we set that equal to the arc length over the entire length of the circle in units. And the length all the way around the circle in units is the circumference, 2 pi r. And so we were able to create a proportion and find that arc length, so that distance from point A to point B around the circle. So today, we're going to take that idea and we're going to apply it to our areas of circles and sectors notes. Now, the definition of a sector of a circle is a region that's bounded by two radii of the circle and their intercepted arc. So I've got the center of circle C right here. I've got a radius r. I've got another radius r over here. And then the intercepted arc AB right here. So this sector is bounded by the two radii and the intercepted arc. It almost looks like a pizza slice, right? That's a sector. So the area of the sector can be found by taking our ideas from yesterday of creating a proportion and applying them to today. But instead of comparing length, we're comparing area. And so we're going to create a proportion. Still part over whole equals part over whole. And we're still going to use the measure of the arc as the part in degrees and the whole circle's degrees as the whole amount. But then we're going to talk about the area of the sector, typically abbreviated A, capital A sub sec for sector, out of the entire area of the circle. Now, the formula for the area of the circle is pi r squared. So this is the proportion that will allow us to calculate the area of a sector of a circle. So in example 1, it says find the area of each sector. Give your answer in terms of pi, meaning leave pi in your answer, and round it to the nearest thousandth. So point something, something, something. So in part A, we want to find the area of sector MPN. MPN. So this sector right here. Now we're given this measurement, which is 3 inches. That's the radius. That 3 inches is also over here because that's also a radius. And then this 80-degree arc measure is the arc measure of arc MN. But what I want to find is that area of the sector. So I'm going to write down my proportion so I can fill in all of the missing pieces. The arc measure out of 360 degrees equals the area of the sector out of the area of the whole circle. And I'm going to substitute the values that I know. So this intercepted arc right here has a measure of 80 degrees, so that's going to get plugged in for n. The area of the sector is unknown. That's what I'm trying to calculate. But my radius is 3 inches. So if I take my radius of 3 and substitute it, 3 squared is 9. So I have 9 pi. When I find the area of the sector, I'm going to cross multiply. So 360 times the area of the sector equals 80 times 9 pi. I'm not going to multiply these together right now because there's no purpose to multiplying them together only to have to break them apart when you simplify. Because now I have to divide by 360 degrees. And my area of the sector, in order to get it, I have to simplify. So I might cross out my zeros. I know that 9 and 36 are both divisible by 9. I know that 8 and 4 are both divisible by 4. So that's a lot of simplifying in order to get an answer of 2 pi. And because this is an area of a sector, I'm measuring in the units squared. So I have my answer in terms of pi. Now I need to find my answer rounded. So I'm sure most of you at home are either using your web browsers or a calculator on your phone. So I'm going to type in 2 times pi. I don't want to type in 2 times 3.14 because 3.14 is not pi, it's an estimation. So 2 times pi gives me a value of 6.2832, and if I round that to the nearest thousandths, this will be 6.283. So the area of the sector equals 6.283 inches squared. So that is my answer rounded to the nearest thousandth. So now I'm going to move on to part B. I'm going to do the same thing. I need to find the area of sector EFG, so EFG, the shaded sector right here. I notice that this radius is 6 centimeters. This radius over here is also 6 centimeters. The radii are the same distance. This angle measures 120 degrees. It's a central angle because its vertex is at the center. That means that its intercepted arc has the same measure as the central angle. So this is also a 120 degree arc. So when I create my proportion, the measure of the arc over 360 total degrees equals the area of the sector out of the total area of the circle. The measure of the arc is 120 degrees. The area of the sector is unknown and what we're solving for. The value of r, the radius, is 6, and 6 squared is 36. When I cross multiply, I get 360 times the area of the sector, and it equals 120 times 36 pi. I divide by 360. I get the area of the sector equals, and then I need to simplify. I can cancel out my zeros. I have a 36 and a 36, which can also be just canceled out, and I'm left with 12 pi. And I'm measuring this in centimeters squared because it is area. Now I also need to find the area of the sector rounded to the nearest thousandth. So I've got my, trying to get it out of the glare, there we go, I've got my calculator. I'm typing in 12 times pi, not 12 times 3.14, just 12 times pi. This is 37.6991, so that rounds to 37.699. And again, I'm measuring in centimeters squared. Okay, so let's see if we can apply these more basic types of problems with our proportion. Let's see if we can apply them to a real-world situation. So in example 2, in agriculture, a circular plot with a 72-foot diameter is watered by a spray irrigation system. So I have a circular plot and it has a 72-foot diameter. Well, I'm not really interested in the diameter. Typically, I need the radius. So how do I find the radius from that? 72 divided by 2 is 36. That's the radius. So I have a 36-foot radius. And the circular plot is being watered by a spray irrigation system. What is the area that is watered as the sprinkler rotates through an angle of 50 degrees? So if I rotate through an angle of 50 degrees, perhaps that's here, and this is 50 degrees. So I'm trying to figure out the area that is watered by that spray irrigation system. So it's like the spray nozzle is at the middle and it's watering all of this. So all of this sector, that's what I need to find the area of. So I'm going to set up my proportion that the measure of the intercepted arc out of 360 degrees is equal to the area of the sector out of the total area of the circle. The measure of the arc right here, it wasn't expressly given to us. However, the measure of the central angle was given to us, and the measure of a central angle is the same as the measure of its intercepted arc. So M is 50 degrees out of 360. The area of the sector we don't know, but we do know that 36 is the radius. So I'm not going to do that multiplication right now, but I am going to say pi times 36 squared is my area of the circle. So I'm going to cross multiply. I have 360 times the area of the sector equals 50 times pi times 36 squared over 360. And now I want to simplify. So I notice that the zeros can cancel. I have a 36 squared, so it's 36 times 36. And there's a 36 down here, so one pair of 36s can cancel out. And I'm left with 36 times 5 times pi. So 36 times 5 is 180, and pi. And my units are feet, so my area is being measured in feet squared. And I wasn't asked for I wasn't asked to provide my answer in terms of pi and rounded to the nearest thousandth, so I just gave an exact answer, which is in terms of pi. So part B of example 2 is similar. It says, what is the area watered in example 2? So same picture. The water in example 2, as the sprinkler rotates now through a semicircle. So instead of my sprinkler rotating just to a 50-degree angle, it's rotating all the way around and it's stopping at a semicircle. So what about this whole arc measure? Think to yourself about that arc measure. What's the arc measure? It's 180 degrees out of 360 degrees. That equals the area of the sector over. We have the same radius, pi times 36 squared. I cross multiply. I get the area of the sector equals 180 times pi times 36 squared over 360. The zeros will cancel. A pair of 36s will cancel. And I will still have an area of the sector that's 18 times pi times 36. And 18 times 36 is 648, and I include pi beside it. I'm measuring in feet for my radius, so I'm measuring in feet squared for the area of the sector. So those are the types of problems that you might see when trying to calculate the area of the sector. Now I'm going to move my paper because now we have a second new term. And this new term is a segment. And we're talking about a segment of a circle, not a segment like segment QR, like that, from one point to another point. So this is not what we're talking about. But a segment of a circle is a region that's bounded by an arc and its chord. The shaded region in this figure is a segment. So this region is bounded by an arc, QR, and the chord that is the segment, QR. And the shaded area in here, that is the segment of the circle. Now, in order to calculate the area of a segment of a circle, in order to calculate this, the area of the segment is equal to the area of the sector minus this little triangle right here. So it's equal to the area of the sector minus the area of a triangle. That's how you calculate the area of the segment. So we have two problems allowing us to practice finding the area of a segment of a circle. So in example 3, it says find the area of the segment. We're trying to find the area of segment ACB. So you really have to be careful that you are understanding what a segment is and what ACB is referring to. It could be referring to angle ACB. It could be referring to sector ACB. It could be referring to lots of different things, but here it is referring to the segment. So if it's not shaded, you need to understand that we're talking about this part right here. Okay? It's kind of like the crust of the pizza, the crust of the sector. So in order to find the area of segment ACB, the area of the segment is equal to the area of the sector minus the area of that triangle. So what I'm going to do is I'm going to find these pieces separately, and then I'm going to subtract them so that I can actually have the area of the segment. So the area of the sector is equal to the measure of the arc. Well, here this arc isn't measured, but the central angle is. So the measure of the arc must be 60 degrees as well. So 60 over 360 equals the area of the sector over the full area of the circle. So pi times r squared. R is 12. So 12 squared. I cross multiply. I get 360 times the area of the sector equals 60 times pi times 12 squared. And I divide by 360. Some nice things happen. The zeros cancel out. Both of these are divisible by 6. One of these 12s is divisible by 6. So we have a 12 left and then a 12 divided by 6, which is 2. So my area of the sector here in this problem is 12 times 2, which is 24, times pi. So that's the area of the whole sector, this whole pizza slice. Now we need to calculate the area of the triangle that we're subtracting out. So this triangle right here, triangle ACB. So I'm going to go ahead and draw triangle ACB. And I know that this is 12 inches, and I know that this is a 60-degree angle, and I also know that this is a radius and this is a radius. So if this is 12 inches, this must also be 12 inches. I have congruent sides here. And what that means is that the sides, the angles that are opposite of those congruent sides are also congruent. Well, if this is 60 degrees and these two have to be the same, what are both of the angle measures? The angle measures must be 60 degrees. So we have an equilateral and equiangular triangle. And in order to calculate the area of the triangle, that formula is 1/2 times the base times the height. So I know the base. The base of the triangle is 12 inches. But what I don't know is the height. So what I'm going to do is draw the height of this triangle at a right angle, keeping in mind that it ends up being like half of this distance. So if this is 12, then this distance is 6. And this is a 60-degree angle, which means this must be a what? A 30-degree angle. And this is a special right triangle. And in our special right triangles, we know that the short side is S, the hypotenuse is 2S, so 2 times 6 is 12, and then the long side is s square roots of 3. Well, if s is 6, then this height right here must be 6 square roots of 3. That is the height of my triangle. So when I multiply everything together, half of 12 is 6, and 6 times 6 square roots of 3 is 36 square roots of 3 inches squared. So in order to calculate that segment, I need to take the area of the sector and subtract from it the area of the triangle. So I have 24, this is the area of the segment, 24 pi inches squared minus 36 square roots of 3 inches squared. Now, it would probably be a better idea to include inches squared at the end and put 24 pi minus 36 square roots of 3 in parentheses. And some people might be a little nervous about leaving this the way that it is, but we should, because it seems like 24 minus 36 is going to give you a negative number. But keep in mind that this is 24 pi. 24 times something more than 3, which will end up giving you something around 75. And we're subtracting from it 36 times the square root of 3. And the square root of 3 is something that's between 1 and 2. So when you subtract, you're not going to get a negative number. And that's important to understand, that it's not 24 minus 36, it's 24 pi minus 36 square roots of 3. And that pi and that square root of 3 make a big difference in number sense. So let's move on to example 3b. Example 3b, I'm going to hope that you can do some parts of this on your own, so I'm going to ask you to do certain parts and then come back and check your work. I need to find the area of segment RST. So this is sector RST right here. But the segment RST is this little bit that's bounded by the arc RT and the chord RT. So this is what I'm trying to find. In order to find the area of the segment, it's equal to the area of the sector minus the area of the triangle. So I'm going to find each of these pieces individually. The area of the sector. I'm going to ask you to pause your video and calculate in terms of pi the area of the sector of circle S and sector RST. So pause your video, calculate the area of the sector, and come back and check your work. You might notice that your measure of arc RT is missing, but you have the measure of the central angle, which happens to be the same as the measure of that intercepted arc. So if this is 90 degrees, then arc RT also has a measure of 90 degrees. When you simplify, you can cancel out your zeros. 9 and 36 are both divisible by 9. 16 and 4 are both divisible by 4, so your area of the sector is 4 pi, and we're measuring in meters squared. Now, I'd like for you to pause your video and calculate the area of the triangle RST that is to be subtracted from that sector. Pause your video and calculate the area of the triangle. Remember that in a triangle, the base and the height are at right angles to each other, so if you just rotate triangle RST around a little bit, you'll have a base of 4 meters and a height of 4 meters, which you can substitute into your formula. Half of 4 is 2, 2 times 4 is 8, so the area of the triangle to be subtracted is 8 meters squared. So what I'd like for you to do finally is pause your video and combine the area of the sector and the area of the triangle in the manner that you're supposed to combine it in order to get the area of segment RST. Pause your video and write your answer. So your answer should have been the area of the sector, 4 pi, minus the area of the triangle, 8, and we measure that in meters squared. So we've extracted and kind of factored out the units out here to the side, and the rest of this is in parentheses. So today we've learned about what a sector of a circle is and a segment of a circle, and we were able to use proportions and our knowledge of circles and area in order to calculate those areas.